not being paid anything, this is a free service, you know that. Okay. So, from curve C in the earlier figure, what we got? We got the Kr as 0.21, which is the upper bound, that is the highest value for that particular cross section which we had seen. But the actual reflection coefficient, what do you expect? We have, I have already told you about the phenomena that is likely to take place. When I say upper bound, the actual reflection coefficient is bound to be smaller than the upper bound, okay. So hence the actual reflection coefficient is going to depend on the wave transmission, then internal dissipation, overtopping and several other factors as I have mentioned earlier, okay. Now revetments faced with armor stone dissipate more wave energy and allows less reflection than smooth slopes. This point is very clear, okay. That is why we have two coefficients. Now since you have the upper bound or the maximum reflection coefficient, in order to get more or less a reflection coefficient close to reality, because it is not so easy to get exactly the reflection coefficient, because you know that it depends on several other parameters like modeling the permeability etc. It is not so easy, okay, and we normally work with an average permeability. So the maximum reflection coefficient which we got has to be multiplied by 2 correction factors, and what are these 2 correction factors? One is when you have the slope, this slope is when it is formed by stones, you see that one correction factor will be because of the slope roughness and also the extent of breaking. There may be some breaking near the toe of the structure. When there is a breaking of waves near the toe of the structure, certain amount of energy is already dissipated. So naturally you see that the reflection, once the energy is dissipated, then you have only lesser energy to act on this, naturally your reflection coefficient has to be small. So that is one kind of a correction factor which is termed as alpha 1. And what is the other correction factor? Later when we discuss the chapter on breakwaters, there we will see how this multiple layers are going to be effective by this multiple layers, but already I have highlighted about the multiple layers earlier, that the bigger size stones will be on the surface, and as you go towards the core of the breakwater, the permeability or the size of the stones will reduce, okay. So in order to account, so you have a kind of this, either you can have 2 layers for the breakwater or for the revetment, or sometimes even 3 layers are used, okay. So to account for the number of layers, we have another factor which is alpha 2. So now you see there are 2 factors which is alpha 1 and alpha 2. I would not go into the theoretical part, because this it would be easier once you know how to apply all these formulas and the procedures etc. In order to arrive at that should be good enough for because the syllabus is quite vast, covering a wide range of topics in the field of coastal engineering. So I would like to avoid this, and if you need any additional information, the best book, best reference would be the Coastal Engineering Manual. Coastal Engineering Manual, I have already mentioned in the reference. So, this is so this book gives a lot of information about all the aspects which I have been discussing in the class. So, let us first consider what is alpha 2. Alpha 2, now you have a as I said, it is based on the number of layers. The alpha 2 is going to be dependent on the number of layers you adopt for constructing your breakwater. So, and that is what you have on the horizontal axis 1, 2, 3, and on the y axis you have another parameter which is dg by hi. dg is the size of the stone which you are going to use for laying the primary layer, and hi, as you know, is the incident wave height. So, this coefficient factor or the correction factor alpha 2 is going to vary as a function of number of layers and dg by hi. So, if you look at the horizontal axis for a particular, for a constant dg by hi, what will you see? You see that as the number of layers increases, the coefficient decreases. This is true because when the number of layers increase, the dissipation is going to be more, and hence the reflection coefficient is expected to be less, and that is what it conveys to you. So, if if in case of this, if dg by hi is increasing, what does that mean? The size is going to increase. If the size increases, more amount of water is going to percolate into the medium. So, the energy is expected to be less, I mean the reflected energy is going to be less, and hence you see that it is also going to decrease with an increase in dg by hi. So, that is that point is very clear. So, let us now what I have already explained h alpha 2. Let us look into this problem and try to understand. So, t equal to 10 seconds, that is the wave with a period of 10 seconds and a height hi equal to 2 meters, impinges on a revetment, having 2 layers, n equal to 2 layers, and dg is also given as 1 meter. Now, the structural slope cot theta is phi, breaker wave height is also provided to you, and then the wavelength at the point of breaking of the wave is 65.2 meters. Okay. What are you expected to find out? You are expected to find out Kr is how much. That is the first problem. The second problem is Kr is 0.1 or 10%, dg is now 0.5 changed from 1. With this, all other parameters are same, so you are supposed to find out n. The third question is Kr is equal to 0.1, n equal to a single layer. Now you are required to find out dg. So just playing with the variables, this makes you to understand the whole problem or the parameters that are involved, and also you, with the help of such problems, you can also understand the effect of the parameters on your objective function, that is here in this case it will be either Kr or whatever it is, but you can easily find out the effect of different parameters. Is that clear? So shall we proceed? So what we need to find out is this parameter dg by L into cot theta. So this will be around 0.62, this is 0.62 for this picture, for this problem. Then you calculate hi by hb, this works out to, see the situation might happen that hb would not have been given to you, but you are given T, you are given hi, okay, you are also given the slope. Now look back at our our discussion on the wave deformation. So if you know the waves beach slope, wave height and wave period, you can definitely calculate your breaker height on your own, okay. And similarly you can also calculate your, once your breaker height is known, your breaker depth can easily be evaluated, you have all empirical relationships, and from that breaker depth you can calculate LB. But here in this problem all these informations are now given to you, but if it is not given you can always calculate. And dg by hi in this case will be 0.5, and epsilon, that is spectral width parameter, the subsimilarity parameter can easily be calculated. We have already seen enough number of problems. So in this case this is going to work out as 1.76. Later you will see that all these dimensionless parameters are required. So now you see, when you are doing your research or when you want to present your own results, it is always good to report in terms of dimensionless parameter. All the parameters which you are looking here are in a dimensionless form, so that will facilitate you to use the kind of nomograms which you can generate for so many for field conditions, for different for range of wave parameters which you have tested in the lab. Now having calculated, remember in the problem it was mentioned revetment. So when it is revetment you use this curve, the top one, which is going to be for plane slopes, and the maximum value for this is for the present, because the subsimilarity parameter is 1.76, so you get the value of Kr as 0.29 from this curve. First let us calculate the value of alpha 1. So you have calculated this value and you have calculated this value. Use this nomogram to arrive at, this gives you the lines of alpha 1 ranging from about 0.95 to 0.2, which depends on the two parameters hi by b and the one which is given on the x axis, along the x axis. These two parameters have been calculated. So now the task 1 of subdivision 1 is completed. Okay. Now we need to get alpha 2. What is alpha 2? Number of layers dg by hi equal to 0.96, number of layers equal to 2. So naturally from this table, which we had already seen, your alpha 2 can be read as 0.93. Is that clear? So alpha 1 and alpha 2 are given, are now found out. Now I call this as kr r suffix, I mean double r I use in order to distinguish from kr. Kr is without the correction factors, but krr is the actual correction factors, actual reflection coefficient after multiplying it by the alpha 1 and alpha 2. Now you see, for this kind of a problem, for this kind of variable parameters, you look at the variation. So what we have got for the upper bound as 0.29, and now you actually get, which is 50% off. So these are all extremely important when you are dealing with kind of coastal rubble mound structures. Coastal rubble mound is also referred to as flexible structures, because the reason is when the wave is acting over the structure, some of the stones get moved and it can be replenished later. Any doubts? Okay, because this problem is quite simple. Now let us move into the next problem. Next problem is, we are having, now kr is 0.1. Now we assume, instead of earlier problem of dg equal to 1 meter, now dg is considered as 0.5 meters. So will this kr change whatever we have evaluated? Because kr, if you look at the surf similarity parameter, it is only the function of beach slope, then hi and t. All these things I have retained the same. So this parameter will be this value will be same, only the values for the correction factor will change, which needs to be evaluated from the figures. So let us follow the same procedure, I do not want to repeat. So for this you calculate dg by hi. dg by hi in this case works out to 0.25 compared to 0.5 in the earlier case. And alpha 1 is picked up from this picture, from this slide, for the corresponding values, and in this problem we have, for p we have alpha 1 equal to 0.38. So what is a KRR? KRR has to be multiplied by the two correction factors with the one without any correction factors. So this can be, this is actually referred to as this is anyway you know, and alpha 1 is 0.38 and KRR is now 0.1, understand? Yes, it is given, KR is given as 0.1. So use this equal to 0.1 and this is known, and you need to calculate what? You need to calculate alpha 2, and in this case alpha 2 will be 0.907. So then once you have the dg by hi which is less than the first column, and this value is coming to around close to 0.9, and hence what is this? This means that the number of layers to be adopted is 2. Naturally you cannot have 2.5 or 2.5 or 2.25 and all, it has to be 1 layer, 2 layers, etc. So this is the second problem. So you see that the subdivision B is answered. Now we will move on to the third one. What is the third one? Third one is n is equal to 1 KRR in fact, okay, this should be KRR is equal to 0.1. So use the same equation. So you see the same equation. For this case alpha 2 can be read as equal to 1, and hence use the above equation to get alpha 1. Alpha 1 now in this case for this particular problem will work out to 0.33, 0.34. But what is hi by B? So use this curve, you have determined alpha 1, you know the value of hi by B, you use this particular curve to get your value of dg by dgl by, okay. So which will work out to 0.54, from which you can easily arrive at the value of dg, and here dg in this case would be around 0.76 meters, okay. Is that clear? So what did we understand? If you want, what you should do is you should go through the slides again. If you have any doubts, go through the slides again in order to understand what we have proved. That is, through problem 1 we have seen that it is over predicted, that is if you are using those curves it is going to be over prediction of reflection coefficient. And we also found out, since for dg equal to 0.5 the number of layers required is 2, and for a single layer the diameter is required is 0.7 meters, 76 meters. So if you are using a single layer the size of the stone might be bigger also. From stability point of view it is always preferred to have more than single layer, and never in such kind of structures you should never be greedy, and also being a miser, trying to be a miser, like you just want to save money and then why should I go for 2 layers, we will just have 1 layer. It might happen one single flood, everything will be, the whole thing can get washed off. Is that clear? So that explains the problem related to reflection when you deal with multiple layers, etc. Now very often you would have a wave propagating from a water depth which is larger to shallower water depth. This change in the bathymetry can also result in reflection. How do you evaluate this? So here you have a wave t equal to 8 seconds, wave height is equal to 2 meters, and it is travelling from a deep water depth of 7 meters to water depth of 2 meters. Maybe the step is approximately 50 meters long, and we need to get the reflection coefficient. So the first step will be, if I call this as a f or whatever it is, then I calculate the parameter, and this will be 5.5. And d1 by d2 is going to be 3.5, and d1 by gt square for the present problem will be 0.011. All simple dimensionless parameter you need to calculate. Once you calculate this, then you need to enter into this nomogram and use that for d1 by d2. What was d1 by d2? 3.5, and d1 by gt square equal to 0.01. Okay. With these values you get into the figure d1 by d2 equal to 3.5, and you see the lines of d1 by gt square, constant lines of constant d1 by gt square. Pick up the value for your 0.01, which is the bottommost curve, and then this is what you will get as the reflection coefficient. See, this is a basic course wherein some of the phenomena and what are all the some of the parameters etc., which we need to consider when you want to go in for real large scale problems involving the field. It may be either through solving through experimental work or solving through numerical work. That is the reason why I have explained with the help of worked out examples, and I hope this will be forming a good base to get started if you are really interested in specializing in this area. Any questions? No questions? Do you have any questions? So this is what I wanted to show, that the estimation of reflection coefficient is much, so the reflected wave height is 0.15. We will get started now with waves and currents. So we are done with reflection diffraction, refraction. And I have also said for practical problems you need to consider the effect of combined reflection, refraction and diffraction. Wherever all these phenomena occur, you have to consider all the phenomena. And similarly, when you are dealing with waves, in locations where you do have the propagation of waves over currents, you need to consider them. Current can flow in the same direction as that of waves, in which we say following currents. We refer to that condition as following current, and we can also have the wave in this direction and the current in this direction, in which case it is referred to as opposing currents. I think we saw in brief what happens to when you have in the same direction or when it goes in the other direction. When we discussed about wave loads on cylinders, when we took the superposition of currents and waves, we found what was happening to the wave loads. The current will influence some of the wave characteristics, and in turn the waves are certain to influence the characteristics of the current. It is vice versa. Now, if the current is in the same direction, I mean the following current, then what will happen? The wave height will decrease and the wavelength will increase. Try to recollect, when we worked out a problem on wave loads on cylinder, for a following current you found that the wave force was increasing. I clearly explained the reasons for this increase in wave force for the following current. If you do not remember, please go back and check my lecture material on wave loads on structures. If the current is in the opposite direction, what will happen? The wave height will increase and the wave length will decrease. The wave frequency will change because the wave celerity is going to change. The wave celerity in the absence of current is C equal to W by K. What is W?
Wave frequency.
2 pi by, that is wave angular frequency, and this one is, so you have L by T. Okay. Now, for currents and waves, celerity is expected to change. Celerity is expected to change. Let me call that as C star equal to C plus U, where C star is the wave celerity in presence of the current. Whenever I use a star, that indicates that waves and currents are propagating together. Okay. U is the, okay. Now frequency will change from W star, which can be written as but C star actually is into K as it is indicated here, which can further be simplified as W plus K into capital U. What is omega star? Omega star is the wave frequency in the case of waves and a current. The component that is superposed now, which is referred to as Ku, is referred to as Doppler effect. So, this is the additional component due to the waves propagating over the current. The current is 0, naturally W star is going to be equal to W or omega in omega. Okay. Is that clear? Shall I proceed? So, if waves are traveling initially in water depth with no mean motion enter a current, certain changes take place in wavelength as well as wave height. If we assume that the number of crests are conserved, you understand, the number of crests are conserved, yeah, on that assumption we can deduce K star equal to U plus U star equal to K into C. One is with the absence of current and another is in presence of the current. So, now for simplicity, in order to understand the characteristics of the waves, we will consider deep water conditions. Always deep water conditions is very easy compared to shallow water conditions, because the effect of depth will not come into picture in deep waters. Just imagine in all these things, if you have the tan HKD which is going to take care of the effect of water depth, then every time you need to deal with that variable, understand. So, herein we are trying to understand what is the effect of current on the waves, on the wave characteristics. It does not matter, we consider just the deep water conditions for simplicity. Okay. So, in that case we can assume that it is in deep waters, and hence you will have that C star square will be G pi K. Okay. So, I will also write this C star equal to G pi, so that you need not have to keep on referring your slides back and forth. Using these equations, all this, you can write, you can get this expression as C star square divided by C square equal to K by K star, which is going to be equal to this. Okay. What is this? This is a quadratic equation in C star by C. It is just a quadratic equation in, so now I can remove all these things, because you have arrived at the final expression, which is going to give you the relationship of the variation in the celerity in presence of currents with that of in the absence of current. Now, this is the final expression which gives that. Now, what is happening with this expression? when the current is flowing in the same direction as that of the waves, that is u will be greater than 0, right. The celerity c star, and when I say c star, naturally the wavelength increases compared to the respective values in the still water, that is without the current. If the waves encounter an adverse current, that is a current in the opposite direction, then your wavelength is decreasing. This is what we have tried to prove. Is that clear? So I will stop here. Okay.